Here we have an amine. Now, are amines nucleophiles or electrophiles?
Nucleophiles.
They're nucleophiles. Why are they nucleophiles? Well, they got a lone pair. Things with lone pairs are generally nucleophiles. Nitrogens are nucleophiles. Even though they don't have a charge, they're pretty decent nucleophiles. They're definitely better than, say, alcohols. Oxygens, neutral oxygens have a lone pair, but they're not really that great as a nucleophile. Remember, you can do an SN1 with an alcohol, but not an SN2. We should try to explain why this is a better nucleophile. So how can we explain why this is the better nucleophile? That is, we're trying to explain why a neutral nitrogen is a better nucleophile than a neutral oxygen. Well, these are these two things in the same column or in the same row of the periodic table? Same row. Nitrogen and oxygen are in the same row of the periodic table. All right, they're both in that same horizontal row. Now, when things are in the same row, I don't know how much we've talked about that. Should you focus on their electronegativity or their size? Electronegativity. In the same row, you focus on electronegativity. Well, is the nitrogen more or less electronegative?
Less.
Less electronegative. Does that make it a better or a worse nucleophile?
Worse. Better.
Better. Because?
It's willing to share the electron.
Yeah. Maybe it would be better to say this is more electronegative. Does oxygen want to hold on to its electrons or donate them?
Keep them.
Yeah, the oxygen that's electronegative wants to hold on to its electrons, so it does not want to act like a nucleophile. The nitrogen is less attached to its electrons, so it's more willing to act like a nucleophile. Remember that a nucleophile would act like this. It would share its electrons with somebody else. Well, oxygen really doesn't want to share its electrons because it's so electronegative. So this is the explanation for why this is a better nucleophile. You're still maybe likely to see on the next test a question that says something like rank things in order of nucleophilicity or something like that. Well, here's one good thought process to go through for that. When things are in the same row, focus on their electronegativity. If things are in the same column, you focus mainly on their size when you're comparing them, but we didn't have to talk about that right here. But in the same row, we focus on electronegativity. So this would be a better nucleophile. As I said, you usually cannot use neutral oxygens for SN2. We saw that last term. But you can use neutral nitrogens for SN2. They're a significantly better nucleophile, even though they don't have a charge. So when you see an amine, one thing you should think about is nucleophilicity and maybe an SN2 reaction. Now, so this is a nucleophile. How about would we think of this as, if this is a nucleophile, would we think of it as a base or an acid?
Base.
Yeah. Again, a base is somebody who would donate electrons and pick up a proton. So this is also a base. We've seen that generally speaking, nucleophiles often are bases, and bases are often nucleophiles, because a nucleophile is somebody who donates electrons. Well, a base has to donate electrons too in order to pick up the proton. Now, to be honest, every once in a while you could treat this like an acid. It is possible to strip away a proton, but it's just very hard. That comes up much less often. This does have protons you could theoretically strip off, but you need a really strong base to do that, so we won't spend time on that. That's not nearly as important. The vast majority of the time, you're going to see this acting like a base. That's going to come up all the time. So we'll focus on how this can be a nucleophile or a base. So both of those are going to be important. Now, this is not a strong base. It's not like sodium hydroxide. You know that if you put in sodium hydroxide, it's going to pick up almost all the protons it can. Or even more, it's not as strong a base as a negative nitrogen. This would again pick up almost all the protons it can. This is called a weak base just in the sense that it partially protonates. But it's still basic enough that we need to focus on that. Do you remember when we talked about carboxylic acids? Did we talk about how since they're acids, they have two different forms, the acid form and the carboxylate form? We said that when you're finishing a carboxylic, when your product is a carboxylic acid, you always have to ask, is the product going to look like this? Or is the product going to look like this? These are the two possibilities. Now, under acidic conditions, which one would it look like?
OH.
Under acidic conditions, it should be protonated. And under basic conditions, it should look like this. This is a place where people oftentimes lose points because they forget to draw the carboxylic acid in the right form. You have to decide what conditions you're in. There's lots of examples of this in the videos that you might be looking at. So that should be a little bit of a review, although I don't know how much we have talked about this, but that's in a lot of the videos. But that same issue should come up for amines, because again, they're basic, so there should be two different forms for an amine. So what's the other form? What would the other form of this look like?
NH minus.
Now let's think for a second. Is the other form here where this has gained a proton or lost a proton?
Oh, gained a proton, so plus NH.
Right, remember this is a base. Remember that it's conceivable this could lose a proton, but that almost never happens. Right. We're going to focus on how this is a base.
So in acidic conditions, it's NH3 plus, and in basic conditions, it's just NH2?
That is correct. That's the right analysis. So for this particular amine, these would be the two forms, and as you figured out, under acidic conditions it would look like this, and under basic conditions it would look like this. All right, so maybe I kind of wrong-footed you because I gave you an example that had both a neutral and a negative form, and maybe you were assuming that there was a negative form here too, but this has both a neutral and a positive form. But that doesn't surprise us because this is an acid and an amine is a base. So it doesn't surprise us that the forms look different for the two of these. So the protonated form of a carboxylic acid is neutral, but the protonated form of an amine is positive. Or the deprotonated form of a carboxylic acid is negative, but the deprotonated form of an amine is neutral. So that's an easy source of lost points that you have to be careful with. Again, theoretically it's possible we could strip away still one more proton from here, but that very rarely happens. Almost always these are the two forms you're going to see as final products. As far as final products are concerned, it's almost always going to be in this category. These are the possible final products for carboxylic acids and for amines. So remember that technically, your final product could either be a carboxylic acid or a carboxylate. It's good to know that the name for this is a carboxylate, carboxylic acid or carboxylate. And theoretically, the final product could either be an amine or an ammonium. So you always have to ask, is the final product carboxylic acid or carboxylate? And is the final product ammonium or amine? And again, it's hard for people to remember that. Well, as you do more practice problems, you'll get comfortable with that. So I expect this will be important on the next test, but this will also be important on the final, because if you've looked ahead in your syllabus, one of the last things you guys are going to be going over is amino acids and peptides. Well, amino acids are called amino acids because on one end, they've got a carboxylic acid group, and on the other end, they have an amine group. So it's important that we learn this material well, because this is going to be important not just for the next test, but also at the end of the class when you guys go over amino acids. Maybe you've already seen this if you've taken some biology. Again, amino acids can have lots of different charges depending on the pH. They can have many different charges depending on the pH, and that's because of these ideas we're talking about here. So we'll get to that more after the next midterm. But even now, we need to know about these possible forms. So in particular, suppose you have both an amine and a carboxylic acid. If you have both an amine and a carboxylic acid, what will happen? Well, the amine will deprotonate the carboxylic acid. So if you start with two things that look like this, you're going to end up with two things that look like this. If your starting materials look like this, your products would look like this. Because what happens when you react an acid with a base? Well, the base deprotonates the acid. Sometimes people, that's such a simple reaction that sometimes people don't even think to do it. But just a simple deprotonation could be what they're going for.